Welcome back, everyone. In this video, I will be continuing the section for the basic properties of derivatives, the power rule, and the exponential rule. All right, so number 4 here, this is going to be the last of our kind of examples of the power rule just by itself. It says, find the points on the curve y equals 2x cubed plus 3x squared minus 12x plus 2, where the tangent line is horizontal. So what does the tangent line being horizontal mean? Well, the tangent line is a line. If it's horizontal, what does that mean its slope is? The slope is 0. So what we're trying to do is figure out when the slope of the tangent line is horizontal. Since the slope of the tangent line is the derivative, we want where the derivative dy over dx or whatever you want to write it as equals 0. So what we're trying to do here is figure out where the derivative of this function is 0, and then we want to give our answers as x, y pairs. And I write that note that there may be more than one, but there could also be none. So there's not a guarantee that any function would have tangent horizontal line. It doesn't have to, but it can also have more than one. All right, so what we'll do, especially with this problem, is we'll graph it after the fact and see how it all works out. All right, so what do we have to do? Well, we want where the derivative equals 0. So let's do the derivative, dy over dx. And the derivative here, this is already in format. We don't have any multiplications or divisions, which means we can just do the derivative. Now, depending on how comfortable you're feeling, you may be comfortable doing this all at once, and that's great if you're there. If you're not there yet, that's okay as well. All right, but think about what we're going to do here. Sort of like when I set up the last problem in the last video, we acknowledge that we're going to do the derivative of each part. We're going to split it up over the pluses and the minuses, and then we're also going to bring the numbers out. So just kind of doing those two steps at once, we would have 2 times the derivative with respect to x of x cubed. So just from the first part, plus 3 times the derivative with respect to x of x squared, second part, minus 12 times the derivative with respect to x of just x, plus, and then this is just a number, so I can leave it as a number, the derivative with respect to x of 2. Right? And hopefully this is looking a little more comfortable. Been practicing it, going through the video. If it's not yet, once again, try to break it down. Can you break it down into 2 steps and get to here? When you split it up over the pluses and minuses, you pretty much should see this exact same thing with the numbers inside, and then you just bring the numbers outside. So the 2 would be in here, you bring it out, the 3 and the 12 and so on. All right. And now what we can do is we can do one of our rules on every single part here. What is the derivative of x cubed? Well, we do the power rule and we bring the power down, the 3, rewrite the x and subtract 1 from the exponent, which is 2, plus the second one, we have a 3 out front and we want the derivative of x squared. Derivative of x squared is 2x. You usually do that one so many times that you just memorize it, but we bring the 2 down. That's where the 2 is coming from. And then when we subtract 1 from the power, it's just 1. So it's not written there. Minus 12 times the derivative with respect to x of x. Well, that thing is derivative of 1. The derivative of x is just 1. And then plus the derivative of a number is 0. Now, eventually, I'm also going to stop writing the 1s and 0s because when we multiply by 1 or add 0, it's not doing anything for us. All right, so let's simplify this. What do we have? We have 2 times 3 is 6, x squared, plus 3 times 2x is 6x, minus 12. This is our derivative. This is the simplified derivative. Now, one thing you may be looking at for the derivative is that, well, we have a 6 everywhere. Can we just factor out a 6? You could factor out a 6, but it's still going to be there. You cannot cancel out a 6. So it's best just to leave your derivative as is. This is our derivative. Right? Now, that's not what we're asked for in this problem, but it was a necessary step. It was necessary to get the derivative. Now, what do we want? We want to figure out when the derivative, our equation here, equals 0. So what we should do is take it 6x squared plus 6x minus 12 and set it equal to 0. Now, when you're set up here, this is where you would definitely want to factor, because we're solving an equation. You have a 6 in common, factor the 6 out. We have take the 6 out, and we got x squared plus x minus 2 equals 0. And can we factor x squared plus x minus 2? Hopefully we can, and we can, because the two numbers that multiply to -2 and add to 1 would be +2 and -1. And now we set each factor to 0. Normally we have to worry about setting the thing in front equal to 0 if there's an x there, but this is just a number, so we don't have to set that part equal to 0. We just have x plus 2 equals 0 and x minus 1 equals 0. And for the one on the left here, you subtract the 2 and you get x equals -2. The one on the right, you add the 1 and you get x equals 1. All right, so what we just figured out, we figured out the x values where the tangent line is horizontal. We still need the y values because you want to give your answer as an xy pair. Now, how do you get the y value? You don't plug it into the derivative because we want the point on the graph. Since we want xy on the graph of y, which is our equation here, we need to plug in x values to the y equation. Y equals 2x cubed plus 3x squared minus 12x plus 2. If we plug in the x, y values here, then we'll be fine. All right, so let's just do -2 first. Plug in -2 here, we get y equals 2 times -2 cubed plus 3 times -2 squared minus 12 times -2 plus 2. Simplify this. -2 cubed is -8 times 2 would be -16. If you want to type it on your calculator and just get a number real quick, that's fine too. -2 squared is 4 times 3 is 12. And then -12 times -2 is +24, then plus 2. And that simplifies all the way to 22. So one of the answers would be x is -22 and y is 22. We're going to have another answer because we do have another x value, which is 1. And the y value here, plug in 1 to our equation for y. And what do we get? Well, every power of 1 is just 1. This is 2 plus 3 minus 12 plus 2. And this would be -5. So our other point is 1, -5. Now what I want to do is just show you what the graph looks like when the tangent line is horizontal. We talked about in a previous section how to really observe where the derivative equals 0, which is what this is doing. But I want to go ahead and do it in Desmos to really confirm that, because that's a very important idea. So y equals 2x raised to the 3 plus 3x raised to the 2 minus 12x plus 2. And I'm going to actually, I can highlight the points here. 1, -5 is down there. And you may have been able to guess that. Let me highlight it. The -2, 22 is up there. How could I have known that right away? Well, when we were trying to graph functions and their derivatives, the way we started is we looked for maximums and minimums, the peaks and the valleys, and that's where the derivative was 0. What we're figuring out in this problem is exactly that. We're figuring out where the derivative is 0. But just, kind of think about what we just did. We didn't use the graph at all to figure out these points. So it's very useful to know that you just did something that before this section, before you start talking about the derivative, there is no possible way to do it besides plugging in numbers, guessing, and hoping to get close to the right number. But also very important to know that when your derivative is 0, it's mostly going to look something like this. There is other possibilities, which we'll see eventually. But when you're looking for what's called maximums and minimums, we're going to be looking where the derivative is 0, and that's useful to know. All right, so to finish up this section, we're going to have one last derivative rule. However, it's to one specific function. It's not to a class of functions. The power rule was for x to any power, the exponential rule is just for e to the x. We're going to need some more rules eventually to talk about exponential function derivatives with a different base from e. But pretty straightforward here. It says let f of x equal e to the x. Then f prime of x also equals e to the x. One of the best derivative rules. Typically students love it because the derivative of f(x) is just itself. The derivative of e to the x, I mean, is just itself. So there are pretty much only two functions that have derivatives equal to the original function itself. It's e to the x and 0. That's a subtle lie because you can have plus and minus numbers on the x and it will still work, but we're not there yet. We're not able to actually do that. Now, what I want to do for this is go ahead and show you that this proof or this formula, just like all the other formulas, which are far more complicated, come from the limit definition of the derivative. So if you want to do the derivative of e to the x, we would have to do, well, let me go ahead and say if f of x equals e to the x, then f prime of x by definition is the limit as h goes to 0 of f of x plus h. F of x plus h would be x plus h in the exponent here. So we'd have e to the x plus h minus f of x, which is just e to the x, over h. And now what do we do from here? Well, the reason why this is something you watch and not actually do yourself is because proving formulas in calculus is usually really hard. And you have to have some inclination as to what to do. Well, your exponent rule, when you have addition here, says you can break up the exponent into two multiplication parts. We're going to get e to the x plus h is the same thing as e to the x times e to the h. We have minus e to the x over h. And the reason that's going to be helpful is you have an e to the x here. In both parts on the top, you can factor out the e to the x. All right, so what it looks like, we have the limit as h goes to 0. We have e to the x, and when we factor that out, for the first term, we have e to the h minus the second term, we have 1 over h. Now, one thing that's really important to observe is that the limit is as h goes to 0. So when we are looking at e to the x, even though we have a variable in it, it's not matching the variable h. We are actually allowed to use that limit rule that says you can move numbers out front. Why can we do that? Because this doesn't have an h in it. We're actually allowed to move this out front. And we get e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And now this limit's actually really hard to do at this point. We'll eventually see an easier way to do it. But what's going on here is that if we graph this, you can see what it's going to be. So what I'm going to do is go ahead and graph this, but I'm going to use y equals. Keep in mind that h is just a placeholder. So when I type x here, I'm not talking about this x at all. I'm just going to graph this function with x instead of h. We have y equals e raised to the x, minus 1 divided by x. And I want the limit as h goes to 0, so x goes to 0, which is at the y-axis. So if I scroll in, what does it look like the limit is? It looks like it's 1. We're traveling along here. We're going towards 1 from the left. We're coming towards y equals 1 from the right. Now it's undefined because we are having division by h here. If we divide by 0, that's undefined, but it is 0 over 0. Right? And what's happening here is that this graph shows us that the limit does equal 1. Like I mentioned before, graphs aren't 100% way, it just gives you an idea of what it is, but this is really hard to show this equals 1 directly. So it's better just to kind of mention it. This limit equals 1, and we end up with our formula. So f prime of x equals e to the x times 1, which is e to the x. Right, now you definitely don't have to know how to prove that. I just wanted to show you, and I'll send reminders with proofs in here every so often. that all these derivative rules are coming from the limit definition of the derivative. They're not random. And we didn't talk about that limit definition of the derivative for no reason. It's just that we kind of want to avoid it as much as possible. It's not easy to deal with, but we just wanted to prove that for you. All right, so now that we have this rule, we can just add it on to our other rules. We have the power rule, we have this one, and then we have the 4 at the beginning, the basic ones. Number 1 says, compute y prime if y equals e to the 4th. Now this one's just another trap because notice here that e to the 4th, this is just a number. It's very easy to look at and think, oh, well, if the derivative of e to the x is e to the x, then the derivative of e to the 4th is e to the 4th. Well, not really, because x is a variable, 4 is a number. E to the 4th is just a number, so that means y prime, when we do the derivative with respect to x or whatever of a number, it's just 0. Okay. So once again, I'm not throwing these at you to trick you. I'm throwing these at you to recognize that just because you have an e to the something, just because you have an exponent, doesn't mean that you're using those rules. You have to make sure you're actually in the correct format. Right, but when it comes to this e to the x rule, since it's pretty much as direct as possible, there's not much we can do with it. At this point, just know that the derivative of e to the x is e to the x and combine it with our other rules. The number 2 here says compute f prime of x if f of x equals 5e to the x minus 2x to the 4th plus 3x minus 1. Now we don't want to throw away all the other derivative rules and all the progress we made here. When we want to do the derivative, we do the derivative of this entire function. Let me go ahead and just write it down. It's already in a format where we're fine to go ahead and proceed because we don't have any multiplications or divisions. We know how to do the derivatives now of e to the x and powers of x. Now, just because we have an e to the x doesn't mean we want to forget about our old rules. We still want to break up and do the derivative each part and then take the numbers that are multiplying out front and put them in front. Okay, so this is going to be when we look at the first term here, we're going to have a 5 in front of the derivative with respect to x of e to the x minus 2 times the derivative with respect to x of x to the 4th plus 3 times the derivative of x with respect to x of just x, and then minus the derivative with respect to x of 1. All right, and we know how to do the derivative of everything in the parentheses now. The derivative e to the x is itself, it's e to the x. That means this is 5e to the x minus, and then the derivative of x to the 4th. Well, we still have to use the power rule there. Right? This new rule doesn't tell us anything about that. We're still using the power rule. And when we do the power rule here, we get 4x cubed. Bring the power down, subtract 1 from the power, plus 3 times the derivative of x is 1. So I'm just going to leave that off because this equals 1. And the derivative of a number is 0. So actually, I don't have to write anything else because this would be times 1 minus 0. Not going to change anything. And there's not much to do here. You can pretty much only do one thing to simplify further. 2 times 4 is 8. That's really it. We get 5e to the x minus 8x cubed plus 3. Now, there's pretty much nothing we could possibly do with this formula because e to the x and x cubed, they're not matching types of functions. We couldn't set this equal to 0 and solve it. That's not possible to do by hand. Really, that's all there is. Now, a lot of what exponentials are used for, which we'll see in the future, is they're used for modeling things in nature. And one of the easiest things to talk about when you're talking about modeling things is exponential growth. Many things have exponential growth or decay. Bacteria is something that exponentially grows usually. It needs like a warm, moist environment. And this is just a general type of formula. It says, suppose the population of a bacteria sample is modeled by the equation y equals p subscript 0 times e to the t power. Now the p subscript 0 it means something. Y is the population after t minutes, and p subscript 0 is the initial population. What we're asked to do is compute the derivative dy over dt, and we're asked what is the rate of change of the population after 8 minutes. Well, we know the rate of change is the derivative, so the second part is asking us find the derivative, which we have to do, dy over dt, and then t is representing the minutes, so then we want to plug in t equals 8. All right, so the first part is telling us to do the derivative. The second part is we have to do the derivative anyway, so we'll have it plug in t equals 8. Now, we don't know what the initial population is. There's nothing we can do about that. But remember that it's just going to be representing a number. All right, so let's do the derivative. dy over dt. We're doing the derivative with respect to t of our y formula here. P subscript 0 e to the t. Now, the thing that's very important to remember is that our variable here is t, which means every other letter that we see is just a number. And that's why I wanted to point that out already. So this p subscript 0 that I've already wrote above, but I'm just going to box in and rewrite. This is just a number. What do we do with numbers if they're multiplying a function? We bring them out front when we do the derivative. We bring it out front, we've got our p0 times the derivative with respect to t of e to the t. Now the derivative of e to the t is itself, so this is actually just p subscript 0 times e to the t power. And if you're looking at that, kind of see, well, the derivative was just the original function. That's not that uncommon because the derivative e to the t is itself, and then it's just being multiplied by a number. It's going to actually be itself. The derivative is itself in this case. Now, what is the rate of change after 8 minutes of the population? Well, all we do is we take our derivative and plug in t equals 8. The way we kind of write plugging in a number when we have this dy over dt notation is we do a vertical bar and write t equals 8. This is just called the evaluation bar. But if you wanted to, you could just plug in t equals 8 here. We get p subscript 0 times e to the 8 power. Not insightful, but it's just not going to be because we weren't told what p subscript 0 is. The idea, though, is that we have this is the rate of change after 8 minutes. Think about what the units would be. Well, we're talking about the population of a bacteria sample. So maybe it's the number of bacteria per minute. Because what's happening is the derivative always gives us a rate of change. The y unit is the bacteria number, and t unit is the time, which is minutes. So it's growing by this many bacteria per minute. And if we had an actual number for p0, we could type it in our calculator and get some sort of estimate. All right, so this is the end of the new material for this section. What I always like to do with derivative rules is just at the end of every section, summarize what you know. And there's kind of 5 things I wanted to talk about to summarize here. What do we know so far? Well, we know we have to break up. One of the things we did every time, we have to break up derivatives over plus and minus. And we have to factor out the numbers, multiplying functions. All right, we did that in every problem, but by the end, what we were doing is we were pretty much doing these 2 steps at once. Another summary at this point, we cannot do derivatives with multiplication or division. We cannot do derivatives with multiplication or division unless we simplify first. And the examples we had in this section, we were able to simplify because we had to actually be able to do them. There are going to be examples in the future where you're not going to be able to simplify. That's why we're going to have a multiplication and division rule for derivatives, but don't want to do too much at once. What else do we know? We know the derivative of two very special functions. It's very useful. The derivative of a number is 0, and the derivative, if your variable is x, but whatever your variable is, it just equals 1. And we know the power rule. The power rule says bring power down and then subtract 1 for new power. Right, and if you like the formula d over dx of x to the n equals nx to the n minus 1. And then the last thing we covered was the exponential rule. It gave us pretty much the derivative of just one specific function. The derivative of e to the x is itself. And in formula, that would be d over dx of e to the x equals e to the x. Right. So we covered a lot in this section, I know, but this is really the breakdown. And hopefully by the end, you were sort of seeing how to consolidate your steps. If we did every single problem breaking down these steps to its very, very detail, there will be problems that you'd probably think about doing close to 30 steps in the future. But if you get used to the steps and then you can sort of see what they're doing individually and then bringing them together like we were at the end, then you can really help yourself save a lot of writing. You just want to make sure you're not breaking any rules. Right? So I hope doing the summary of the derivative rules so far in every section is helpful. It was something that when I was learning the derivative rules, I thought there were so many of them, and it just ended up feeling like a long list of formulas. So I hope by summarizing them at the end of every section, it helps you realize what you're doing as you go through. But I'll see you in the next video.